In this lesson, you will learn how to integrate all components from the IoT system into a single cohesive project. Specifically, we will combine the TFT local display with the web server, allowing the ESP32 to display data both on the physical screen and via a web server. This integration is crucial because it demonstrates how IoT devices can interact with multiple interfaces simultaneously, providing both local and remote access to data. By the end of this lesson, you will have a fully integrated IoT system that updates real-time temperature and humidity data on both the TFT display and the web server. So far, you have learned how to set up a TFT display, how to show sensor data, and how to set up a dynamic web page on a hosted web server. Now it is time to combine all of these functionalities, allowing the ESP32 to handle both local display and remote web server duties concurrently. This step demonstrates the power of the ESP32 in IoT applications. This versatility is what makes the ESP32 such a strong choice for IoT applications. So let's quickly recap the two key components we will be combining. The TFT display. The TFT display is a small screen that shows real-time data, such as temperature and humidity readings, directly onto the IoT device. This provides immediate local feedback, making it useful in scenarios where direct contact with the device is needed. The web server allows the ESP32 to share data over Wi-Fi. This makes the data accessible to any device connected on the same network, such as phone, tablet, or computer. This capability enables remote monitoring, a key feature of many IoT systems. In this lesson, we will merge these two components into a single integrated system. Now that we have an understanding of how each component works individually, let's combine them into one program. We're going to be building on the previously written web server code. For starters, we will be including the necessary library, and that is the tft_espi.h library that we will be using for the TFT display. We will move past all of the web server and network credentials, and we will create an instance of the TFT display. We have done this before by employing the included library. Now we move further down for the AHT10 sensor, and we will be adding new variables. AHT_humidity, and of course for temperature. Besides that, we will also be creating some vary floats for the temperature and for the humidity. Now, in the handle root, we will need to do some modifications. This is primarily removing the sensor event completely. This will be formatted and included into the setup function. We will also be changing the temp.temperature to just temperature to reflect the new variable created, and the humidity as well. If we had kept the temperature in the string, we would have had a local variable. This means that the data from the sensor would only be accessible within the handle root function. While we do not want that, we have created some global variables that are outside of any function and can be accessed both by the handle root, setup, and loop functions. No other changes will be done to the handle root, and we can move on to the setup. We keep the sensor initialization as it is, and also the Wi-Fi setup. After it has connected to the Wi-Fi, but before the web server was started, we are going to start initializing our TFT display. The code will be formatted exactly like we did in the enhancing the output lesson. So we have tft.init, we have tft fill screen, we have tft set color, And we have TFT sets text size. Great. Before moving forward, we also need to put data into the variables that we have created at the beginning. So aht_temp equals aht.get temperature sensor. Great. And of course aht_humidity aht.get humidity sensor. Now we are done with the void setup, so let's move down to the loop. So first we will get the sensor readings by using sensors_event t temp event, and of course the humidity event. The aht_temp that we have created earlier will receive the get event, temp event, and the same will happen with the aht_humidity. Now that we have finished getting the data from the sensor, it's time to populate the floats that we created at the beginning. Relative humidity. Great, now that we have gotten our data, it's time to recode the UI that we did in previous lessons. I will code it by hand, but you can feel free to go and copy it. So first we will clear the screen with the TFT fill screen. Then we will display temperature data with a background color. This first variable was cyan, rounded rectangle. This goes TFT fill round rect. We're going to use the same variables, 5 pixels from the left, 15 pixels from the top, 130 pixels wide, 100 pixels long, and a curvature at the corners of 5 pixels. And of course the TFT cyan color. Now we will be setting the text color to black to contrast with the background. We're going to do that by using the tft.setTextColor to tft_black. Now we have the input of the actual data, tft draw string. We're going to keep everything the same. Temp, 10 pixels from the left, 25 pixels from the top, and a font size of 2. Then again tft draw string, and this time we will actually input the actual temperature string of temperature, and of course inside a comma and a 1 to signify that we only wanted to have 1 decimal place after the comma. Then we have 10 pixels from the left, 55 pixels from the top, and a font size of 4. Again tft draw string. It's great to type them all again because that way you remember the commands easier. We're going to input our small little unit at 110 from the left, 65 from the top, and a font size of 2. So everything fits neatly into the screen. And we are done with the temperature. Now let's go over and display the humidity data, also with a background color. This one will be a yellow rounded rectangle. We'll do that by aligning everything first of all, and then of course TFT fill round rect, and we're going to make it TFT underscore yellow. We set the text color to black, and we set the text size to 2. The reason why we are doing this every single time, setting the color, setting the size, while we also set a white color over here and then change it to black, is because we need to initialize the TFT display with one specific color. This is done so you can have multiple colors for multiple different sections of the display. You can have one text be white, one text be black, but to make sure that it's initialized in white, since the screen is black, we put that in the beginning. Now let's finish up in here with a TFT draw string. Now we'll do the humidity at 10 pixels from the left, 135 from the top, and a font size of 2. Then we have a TFT draw string, and we turn the humidity readings into a string, humidity, of course another (-1) to signify that we only want one decimal place, 10 pixels from the right, 165 from the top, a font size of 4, and all we have to do now is input the last drawstring percentage symbol at 110 from the right, 175 from the top, and a font size of 2 to have it be smaller. And of course we are going to need a simple, small, tiny delay. This delay will only be of 1000 milliseconds. The reason why we make it to be 1000 milliseconds is because up here in the meta HTTP equiv, we set it to refresh the website every 5 seconds. The website is being refreshed every 5 seconds, and the whole code, because the delay is not only for the screen, but since it's in the loop function, it delays the loop function. So having 2 5-second delays will make the web server crash and the connection to show as terminated. Now everything has been initialized successfully. This should be it. Amazing. Let me put in my credentials and upload it. Now, while this uploads, let's go over what is going on in the code. So we import the needed libraries. Then we also create all of the objects needed for this project, as well as the variables. We create a web server, the TFT display, the AHT humidity sensor and temperature sensor. And of course, we create global variables to be accessed both by the web server and the TFT display. In the handle root, we do exactly what we have done yesterday. This creates a HTML text file that will be forwarded to the web server when the client sends an HTTP request. After that, we connect to the Wi-Fi network using the Wi-Fi.begin function. We wait until the ESP connects, and when it's successful, the IP address is printed in the serial monitor. The IP address again is essential because this is how we will access the web server from another device. After that, we initialize the TFT display. We read data from the AHT10 sensor using the Adafruit library. And of course, we set up a basic web server, just like in previous lessons. The web server listens for requests at the root URL and responds with dynamically generated HTML containing the latest temperature and humidity readings. After that, we populate the global variables with the sensor data. We update the TFT display to show the most recent sensor data. The screen is cleared and updated with the latest temperature and humidity readings every second. And then of course the server.handleClient function listens for the incoming HTTP requests. So basically what we did in this lesson is go over everything that we have learned until now. Initializing the sensor, reading data and storing it, initializing the TFT display, displaying text on it, and then displaying dynamically updated data, set up a web server, connect to Wi-Fi, and display dynamic data on the Wi-Fi server. Now everything is combined into one cohesive IoT project. Once the code is uploaded to your ESP32, you can open up the serial monitor to confirm that the ESP32 has successfully connected to the Wi-Fi network. Also remember to get the IP address from the serial monitor. We will need this in order to access the web server. So this will also be 5 pixels from the left, 130 from the top, 130 in width, 100 in length, and with a corner radius of 5 pixels. Error messages are very helpful. Now that it's done uploading, let's check the serial monitor. Let's of course reset the display. And we can see that the sensor has initialized, is connected to Wi-Fi, we have an IP address, and the web server has started. Now as you can see, the data is being updated every 5 seconds, just until now, the only difference being that the display is also updating with needed data. As you can clearly see, it's also updating on the ESP32. We are getting readings of 27.6 or 27.7, which is exactly the same as on the website. Remember to confirm that the values displayed on the TFT screen and the values on the web page are the same. Both should update in real time, ensuring that the data is being displayed properly, both locally and remotely. Some common issues may include the web page not loading. For that, you should double check the IP address of the ESP32 in the serial monitor and ensure that the ESP32 is still connected to the Wi-Fi. If you're having some TFT display issues, ensure that the TFT display is properly initialized in the code. If the display does not update, check for loose wires and verify that the correct pins are being used. And of course, if the sensor data is not appearing, whether it be on the web page or the TFT display, check the connections and ensure that the sensor is properly initialized in your code. This lesson has demonstrated how to combine multiple functionalities into a single IoT system. By integrating a local display with a remote server, you have created a dual interface system that is more versatile and accessible. This approach is particularly useful for applications where data needs to be monitored both locally and remotely. For example, in an environmental monitoring station, the local users can view the data directly on the device, while remote users can access the same data via the network. This ensures that critical information is always available, regardless of location. So congratulations, in this lesson you have successfully combined the TFT functionality, the AHT10 sensor, and the web server, creating a fully integrated IoT system capable of displaying real-time sensor data both locally and over a web server. This is a significant step towards building a complex, versatile IoT system capable of serving multiple interfaces simultaneously.